Learning objectives. In this chapter, the user would learn the following in detail: monocular imaging system, orthographic and perspective projection, camera model and camera calibration, stereo and multi-view geometry, binocular imaging systems. Image formation. The study of image formation encompasses the radiometric and geometric processes by which 2D images of 3D objects are formed. The image formation process also includes analog to digital conversion and sampling. The two parts of the image formation process. The geometry of image formation, which determines where in the image plane the projection of a point in the scene will be located. The physics of light, which determines the brightness of a point in the image plane as a function of illumination and surface properties. A simple model. The scene is illuminated by a single source. The scene reflects radiation towards the camera. The camera senses it via chemicals on film. At the surface of the apple, light is reflected in all directions, and two of the rays hit the eye of two observers. Camera geometry. The simplest device to form an image of a 3D scene on a 2D surface is the pinhole camera. Rays of light pass through a pinhole and form an inverted image of the object on the image plane. Camera optics. In practice, the aperture must be larger to admit more light. Lenses are placed in the aperture to focus the bundle of rays from each scene point onto the corresponding point in the image plane. Diffraction and pinhole optics. If we use a wide pinhole, light from the source spreads across the image, that is, not properly focused, making it blurry. If we narrow the pinhole, only a small amount of light is let in. The image sharpness is limited by diffraction. When light passes through a small aperture, it does not travel in a straight line. It is scattered in many directions. This is a quantum effect. In general, the aim of using lens is to duplicate the pinhole geometry without resorting to undesirable small apertures. Human vision. At high light levels, pupil aperture is small and blurring is due to diffraction. At low light levels, pupil is open and blurring is due to lens imperfections. CCD cameras. An array of tiny solid-state cells convert light energy into electrical charge. Manufactured on chips typically measuring about 1 cm by 1 cm, for a 512 × 512 array, each element has a real width of roughly 0.001 centimeters. The output of a CCD array is a continuous electrical signal, video signal, which is generated by scanning the photosensors in a given order, that is, line by line, and reading out their voltages. Frame grabber. The video signal is sent to an electronic device called the frame grabber. The frame grabber digitizes the signal into a 2D rectangular array n into m of integer values stored in the frame buffer. CCD array and frame buffer. In a CCD camera, the physical image plane is the CCD array of n into m rectangular grid of photosensors. The pixel image plane, frame buffer, is an array of n into m integer values, pixels. The position of the same point on the image plane will be different if measured in CCD elements x, y or image pixels xim, yim. In general, small n is not equal to n, capital, and small m is not equal to capital M. Assuming that the origin in both cases is the upper left corner, we have xim equals capital N divided by small n x yim equals capital M divided by small m y, where xim, yim are the coordinates of the point in the pixel plane and x, y are the coordinates of the point in the CCD plane. In general, it is convenient to assume that the CCD elements are always in one tone correspondence with the image pixels. Units in each case. xim, yim is measured in pixels. X, y is measured in millimeters. Reference frames. 5 reference frames are needed for general problems in 3D scene analysis. Transformations between frames. Object coordinates 3D, world coordinates 3D, camera coordinates 3D, image plane coordinates 2D, pixel coordinates 2D. Object coordinate frame. This is a 3D coordinate system xb, yb, zb. It is used to model ideal objects in both computer graphics and computer vision. It is needed to inspect an object, that is, to check if a particular hole is in proper position relative to the other holes. The coordinates of 3D point B, that is, relative to the object reference frame, are xb, 0, zb. Object coordinates do not change regardless of how the object is placed in the scene. Notation: x0, y0, z0 into t. World coordinate frame. This is a 3D coordinate system xw, yw, zw. The scene consists of object models that have been placed, rotated and translated into the scene, yielding object coordinates in the world coordinate system. It is needed to relate objects in 3D, that is, the image sensor tells the robot where to pick up the bolt and in which hole to insert it. Notation: xw, yw, zw into t. Camera coordinate frame. This is a 3D coordinate system xc, yc, zc axes. Its purpose is to represent objects with respect to the location of the camera. Notation: xc, yc, zc into t. Image plane coordinate frame CCD plane. This is a 2D coordinate system xf, yf axes. Describes the coordinates of 3D points projected on the image plane. The projection of A, that is a point whose both coordinates are negative. Notation: x, y into t. Pixel coordinate frame. This is a 2D coordinate system r, c axis. Each pixel in this frame has integer pixel coordinates. Point A, that is, gets projected to the image AR, AC, where AR and AC are integer row and column. Notation: xim, yim into t. Binocular imaging system. In binocular vision, two eyes work together to focus on a single point. Advantages of binocular vision. It gives a creature a spare eye in case one is damaged. It gives a wider field of view. It can give two eyes different positions. It allows the angles of the eye's line of sight relative to each other and those lines relative to a particular object to be determined from the images in the two eyes. These properties are necessary for the third advantage. It allows the creature to see more of or all of an object behind an obstacle. This advantage means that a vertical column closer to the eyes than an object at which a creature is looking might block some of the object from the left eye, but that part of the object might be visible to the right eye. It gives the ability to detect faint objects with enhancement. Binocular depth perception. Binocular disparity. Differences between the images falling on the two retinas. Convergence. Eyes turn inward, reduces disparity of the feature to 0 or near 0. Divergence. Eyes turn outward, reduces the disparity of the feature to 0 or near 0. Binocular cue. Convergence. The angle between the line of sight of each eye is larger as an object moves closer. It will work for nearby images. Retinal disparity. Each eye receives a slightly different view of a scene. The two views are used to determine the ratio of distances between nearby objects. For example, close one eye and position your thumb so that one blocks the other with 1 centimeter distance between them. Switch to your viewing eye. Open both eyes. What is the difference between binocular and monocular? When signals from the two eyes reach the brain, they are superimposed and processed into a single picture with depth. As a result, we get a 3D picture and are able to judge distances well. Most birds and lizards have monocular vision. Their eyes are on each side of their head. Can you drive if you are blind in one eye? Yes, you may still be able to drive a car or motorcycle if you have only one eye, or sight loss in one eye, sometimes called monocular vision. This is provided that the DVLA is satisfied that you have sufficient sight in your other eye, including a normal field of vision. What kind of animals have binocular vision? Usually, but not always, predatory animals have the two eyes positioned on the front of the heads, thereby allowing the binocular vision and reducing their field of view in favor of stereopsis. Other than humans, the examples include eagles, wolves, and snakes. Is relative size a binocular depth cue? Convergence and binocular parallax are the only binocular depth cues. All others are monocular. The psychological depth cues are retina image size, linear perspective, texture gradient, overlapping, area perspective, and shades and shadows. Camera model and calibration. Camera calibration. Finding camera's internal parameters that affect the imaging process. 1. Position of the image center on the image, usually not just width by 2 or height by 2. 2. Focal length. 3. Scaling factors for row and column pixels. 4. Lens distortion. Calibration procedure. Calibration. Finding the function defined by the camera that maps 3D points to a 2D image plane. First thing required is to obtain pairs of corresponding 3D and 2D points. Capital X1, Y1, Z1 into small x1, y1, capital X2, y2, z2 into small x2, y2, and so on. Calibration target. Two perpendicular planes with chessboard pattern. We know that the 3D positions of the corners with respect to a coordinate system defined on the target. Place a camera in front of the target and we can locate the corresponding corners on the image. This gives us the correspondences. Recover the equation that describes imaging projection and camera's internal parameters. At the same time, also recover the relative orientation between the camera and the target. Finding corners. Corner detector. Canny edge detector plus fitting lines to the detected edges. Find the intersections of the lines. Manual input. World coordinates and camera coordinates. Matching 3D and 2D points, we know the number of corners by counting. This gives corresponding pairs. World point is equal to image point. Capital X1, Y1, Z1 is equal to small x1, y1. XS, YS, ZS is a world coordinate frame. Small xs, ys, zs is known as the image coordinate frame. T is known as a translation vector. I, J, K are known as vectors of rotation matrix. Please refer to the diagram on screen and the rotation matrix. Rotation matrix. (3D rotation). Linear algebra definition. A matrix R is a rotation matrix if and only if it is an orthogonal matrix with determinant +1. Orthogonal matrix. A square matrix with real entries whose columns and rows are orthogonal vectors with length 1. That means R to the power of t equals I, or R to the power of -1 equals R to the power of t. 3D transformations, rotation. Rx, Ry, Rz are known as rotational matrix. Thus, Euler angles for rotation R equals Rz, Ry, Rx can be represented as rotation by psi about the z-axis, Rz equals cos psi sin psi 0 minus sin psi cos psi 0, 0, 0, 1. Rotation by theta about the y-axis, Ry equals cos theta 0 minus sin theta, 0, 1, 0, Sin theta, 0 cos theta. Rotation by pi about the x-axis, Rx equals 1, 0, 0, 0 cos pi, sin pi, 0 minus sin pi, cos pi. Sequence not standardized. Homogeneous coordinates. Suppose we have a point x, y, z in the Euclidean plane. To represent the same point in the projective plane, we simply add a third coordinate of 1 at the end. X, y, z, 1, and so on. Overall scaling is unimportant, so the point x, y, z, 1 is the same as a point for any non-zero equation. Please refer to the matrix of homogeneous coordinates on screen. Perspective projection. Using homogeneous equation, the perspective projection becomes linear. Thus, the equations of a perspective projection, center of projection C, are represented in the diagram attached and the matrix. Thus, the equations of perspective projection is as represented in the diagram shown. Pixel coordinates. Transformation uses image center x0, y0, scaling factors kx and ky. Please refer to the pixel coordinates matrix shown on screen. Calibration matrix. Calibration matrix, which is used to convert 3D pictures into 2D images. K is called as calibration matrix. From the image on screen, alpha x and alpha y are focal lengths in pixels. x0 and y0 are coordinates of image center in pixels. Added parameter s is Q parameter. Please refer to the matrix on screen. Putting everything together, here, x equals px. Calibration matrix is shown on the screen. Calibration. Estimate matrix P using scene points and their images. Estimate the intrinsic and extrinsic parameters. Left 3x3 submatrix is the product of an upper triangular matrix and an orthogonal matrix. P equals Kr into matrix of I3 minus C cap. Computing matrix P. Use corresponding images and scene points, 3D points xi in the world coordinate system, images of small xi of capital Xi in image. Thus, small xi equals P into capital Xi for all I values. Xi equals P capital Xi involves homogeneous coordinates. Thus, Xi and Pxi just have to be proportional. Xi equals Pxi equals 0. Let P1t, P2t, P3t be the 3 rows of vectors of P. Please refer to the calibration matrix shown on screen. Third row can be obtained from sum of ui times first row vi times second row. So we get 2 independent equations in 11 unknowns. With 6-point correspondence, we get enough equations to compute matrix P. AP equals 0. Linear system AP equals 0. When possible, have at least 5 times as many equations as unknowns. Minimize mod of AP with the constraint mod of P equals 1. P is the unit singular vector of A, corresponding to the smallest singular value. Thus, A equals UdV transpose is the SVD of A. Computing the translation component. Find homogeneous coordinate of C. C is the null vector matrix of P. Thus here, PC equals 0 and P equals KR mod of I3 minus C cap. KR mod of I3 minus C cap equals P. Please refer to the matrix shown on screen. Find null vector C of P using SVD. C is the unit singular vector of P corresponding to the smallest singular value. Camera matrix decomposition. Finding the camera orientation and internal parameters. QR decomposition. QR decomposition of a matrix is a decomposition of the matrix into an orthogonal and a right triangular matrix. Please refer to the equation on screen. Further improvement used as initialization for nonlinear minimization of summation of I d of xi, pxi whole squared. Most popular nonlinear minimization algorithm is the Levenberg. Marquardt minimization LM is more robust to local minima than, for example, the Gaussian-Newton algorithm and the method of gradient descent. Advanced calibration, nonlinear distortions, barrel and pincushion, tangential. Models of radial distortions. Please refer to the matrix and the diagram on screen. Direct linear calibration. Advantage: very simple to formulate and solve. Disadvantages: doesn't tell you the camera parameters. Doesn't model radial distortion. Hard to impose constraints, for example, known focal length. Doesn't minimize the right error function. For these reasons, nonlinear methods are preferred. Define error function E between projected 3D points and image positions. E is nonlinear function of intrinsics, extrinsics, and radial distortion. Minimize E using nonlinear optimization techniques. For example, variants of Newton's method, that is, Levenberg-Marquardt. Advantage: only requires a plane. Doesn't have to know positions or orientations. Calibration using CAD model. It is used to reduce number of interactions. Pre-compute as much parameters as possible. More stable. Less user input required. Monocular imaging system. Monocular vision is a vision in which both eyes are used separately. By using the eyes in this way as opposed to binocular vision, the field of view is increased while depth perception is limited. Monocular vision. Anomalous trichomacy. They are able to see colors in all three ranges because their eyes have all three types of cone cells. The anomalous trichomat uses three cones in different proportions from the normal trichomat. They are not as capable of discriminating between similar colors or detecting slightly different shades. 2D, 3D relations. Difference between multi-view and single-view analysis. Different emphasis on the relative importance of measurement and prior knowledge. Depth ambiguities. Self-occluded body parts. Similar techniques at least one way. Transition monocular, that is multi-view straightforward. Monocular as the robust limit of multi-view. Multiple cameras unavailable or less effective in real-world environments due to occlusion from other people, objects, etc. Difficulties. High dimensional space, 30 to 60 df. Complex appearance due to articulation, deformation, clothing, body proportions. Fast motions only vaguely known a priori. Data association. Characterizes the space of solutions assuming 2D joint positions plus limb lengths. Internal camera parameters. Builds an interpretation tree of projection-consistent hypotheses. Third joint positions. obtained by forward-backward flips in depth. O2 of body parts solutions, in principle, can prune some by physical reasoning, but no procedure to compute joint angles, hence difficult to reason about physical constraints. Not an automatic 3D reconstruction method. Select the true solution out of many manually. Adapted for orthographic cameras. Monocular static pose optima. It has 2 power nr of joints. Some pruned by physical constraints. Temporarily persistent. Trajectory ambiguities. General smooth dynamics. Ambiguities images called as reversible figures. Reversible figures are optical illusion images which exploit graphical similarities and other properties of visual system interpretation between two or more distinct image forms. Latent coordinate and latent space. Latent coordinate, interpretation 1, points at camera when conversation ends. Interpretation 2, it says salute when conversation ends. The nature of 3D ambiguities. Persistence over long time scales. Loops A, B, C have limited time scale support, hence ambiguity cannot be resolved by extending it. Generative versus discriminative modeling. Generative modeling predicts state distributions from image features. Learning to invert perspective projection and kinematics is difficult and produces multiple solutions. Multi-valued mappings identical to multimodal conditional state distributions. Temporal extensions necessary. Top-down approach. Model the observation. Discriminative modeling. Optimize alignment with image features. Can learn state representations, dynamics, observation models, but difficult to model human appearance. State interference is expensive, need effective optimization. Bottom-up approach. Condition on the observation. X is the model state R, our image observations. Goal, P theta of X by R, where theta is a parameter to learn given training set of R, X pairs. P theta X by R is directly proportional to P theta of R by X into Px. Model-based multi-view reconstruction. Body represented as textured 3D mesh. Tracking by minimizing distance between 3D points on the mesh and volumetric reconstruction obtained from multiple cameras. Generative 3D reconstruction annealed particle filter. Careful design. Dynamics. Observation likelihood. Annealing-based search procedure improves over particle filtering. Simple background and clothing. Generative 3D reconstruction. Consideration base filter. Dynamical models. Careful learning of observations, likelihood distributions. Non-parametric belief propagation, initialization by limb detection and triangulation. Kinematic jump sampling. Kinematic sampler is a main specific sampler where each configuration of the skeletal kinematic tree has an associated interpretation tree. Used in conjunction with nonlinear mixture smoothers. Example, intrinsic dimension estimation and latent representation for walking. 2,500 samples from motion capture. The Hausdorff dimension, D, is effectively 1, lift to 3 for more flexibility, to learn the latent third space embedded in an ambient 30D human joint angle space. The intrinsic dimension estimation equation is shown on the screen. 3D model-based reconstruction. Track human joints using the WSL tracker. Optimize model joint reprojection error in a low-dimensional space obtained using probabilistic PCA. Nearest neighbor parameter sensitive hashing, PSH, relies on database observation state pairs rendered artificially. Locates samples that have observation components similar to the current image, data, nearest neighbors, and use their state as putative estimates. extension to multiple cameras and tracking by nonlinear model optimization, foreground-background segmentation from stereo. Regression methods. A post-recovery by nonlinear regression against silhouette observations represented as shape context histograms, emphasis on sparse, efficient predictions, good generalization. Careful study of dynamical regression-based predictors for walking and extensions to mixture of regressors. E&L pose from silhouette regression where the dimensionality of the input is reduced using nonlinear embedding. Latent input to joint angle output state space map based on RBF networks. Specialized mappings architecture. Static 3D human pose estimation from silhouettes. Human movements. Approximates the observation pose mapping from training data. Mixture of neural networks. Models a joint distribution. Uses the forward model, graphics rendering, to verify solutions. Conditional Bayesian mixtures of experts. A single expert cannot represent multi-valued relations. Multiple experts can focus on representing parts of the data, but the expert contribution importance is contextual. Disregarding context introduces systematic error, invalid extrapolation. The experts need observation-sensitive mixing proportions. Discriminative temporal interference. Bottom-up chain, condition on the observation. The temporal prior is a Gaussian mixture. The local conditional is a Bayesian mixture of Gaussian experts. Integrate pairwise products of Gaussians analytically. As shown in the following equation. Local conditional, temporal filtered prior, low-dimensional discriminative interference. The post-prediction problem is highly structured. Human joint angles are correlated, not independent. Learn conditional mixtures between low-dimensional spaces decorrelated. Sources of depth perception. Please refer to the diagram shown on screen. Depth perception. Ability to detect how far away an object is from other objects. Monocular vision. A condition in which one eye is blind, seeing with only one eye. Binocular vision. Seeing with two eyes simultaneously. Light from a single point of a distant object and light from a single point of a nearest object being brought to a focus by changing the curvature of the lens. Euclidean geometry. Parallel lines remain parallel when extended in space. Even though curved on the retina, objects stay same size and shape. Monocular depth cues. Accommodation or focusing. It is a change in dioptric power of the interocular lens in order to see a near object more clearly. More the accommodation needed, the closer the object. Accommodation and convergence depth perception of monocular shown in figure. Linear perspective. The visual phenomenon in which parallel straight lines will converge in the distance. If two parallel lines are assumed to be straight, then the further separated the lines become, the closer the object must be. Interposition or overlapping. It is the visual phenomenon in which the view of one object may be blocked by another object. The object being blocked must be behind the first object. Texture gradient. The amount of detail in an object. The closer the object, the more detail visible. Far objects lose detail. Relative size. Relative size is the visual phenomenon in which larger retinal image sizes are associated with objects that are closer. An object that appears larger than a similar object will be closer. Light and shadow. These cues can provide feedback on the elevation or recession of an object. Relative brightness. Relative brightness is the visual phenomenon in which closer objects appear brighter than further objects. Aerial perspective. Aerial perspective is the visual phenomenon of distant objects appearing hazier than closer objects. This only occurs in long distances, like mountains which appear hazy due to how far away they are. Motion parallax. Motion parallax is the apparent displacement of objects in space while moving that causes closer objects to move faster than distant objects. Orthographic and perspective projection. Orthographic projection. Orthographic projection is a way of drawing a 3D object from different directions. Usually a front, side, and plan view are drawn so that a person looking at the drawing can see all the important sides. Perspective projection. When an object is viewed from different directions and at different distances, the appearance of the object will be different. Such a view is called perspective view. It is very important for commercial purposes. Pinhole camera and perspective projection. This is the simplest imaging device which captures accurately the geometry of perspective projection. Rays of light enter the camera through an infinitesimally small aperture. The intersection of the light rays with the image plane form the image of the object. Such a mapping from 3 dimensions onto 2 dimensions is called perspective projection. A simplified geometric arrangement. In general, the world and camera coordinate systems are not aligned. To simplify the derivation of the perspective projection equations, we will make the following assumptions. 1. The center of projection coincides with the origin of the world. 2. The camera axis, optical axis, is aligned with the world's z-axis. 3. Avoid image inversion by assuming that the image plane is in front of the center of projection. Some terminology. The model consists of a plane, image plane, and a 3D point O, center of projection. The distance f between the image plane and the center of projection O is the focal length, that is, the distance between the lens and the CCD array. The line through O and perpendicular to the image plane is the optical axis. The intersection of the optical axis with the image plane is called principal point or image center. Note: the principal point is not always the actual center of the image. Equations of perspective projection. Notation: x, y, z equals capital X, y, z. R equals capital R, x dash, y dash, z dash equals x, y, z. R dash equals R. Using following similar triangles. 1. From OA dash B dash and OAB, f by z equals R by capital R. From A dash B dash C dash and ABC, x by capital X equals small y by capital Y equals small r by capital R. Perspective projection equations. X equals xf by z, y equals yf by z, z equals f. Using matrix equation, xh yh zh equals f 0 0 0 0 f 0 0 0 0 f 0 0 0 1 0 into capital X, Y, Z and 1. Verify the correctness of the above matrix. Homogenize using W equals Z. X equals XH by W equals FX by Z. Y equals YH by W equals FY by Z. Z equals SH by W equals F. Properties of perspective projection. Many-to-one mapping, scaling, effect of focal length, lines of distance angles, vanishing point, vanishing line. Many-to-one mapping. The projection of a point is not unique. Any point on the line OP has the same projection. Scaling. The inverse of an object is inversely proportional to its image size. When a line or surface is parallel to the image plane, the effect of perspective projection is scaling. When a line or surface is not parallel to the image plane, we use the term foreshortening to describe the projective distortion. That is, the dimension parallel to the optical axis is compressed relative to the frontal dimension. Effect of focal length. As f gets smaller, more points project onto the image plane, wide-angle camera. As f gets larger, the field of view becomes smaller, more telescopic. Lines, distances, angles. Lines in 3D project to lines in 2D. Distances and angles are not preserved. Parallel lines do not in general project to parallel lines unless they are parallel to the image plane. Vanishing point. Parallel lines in space project perspectively onto lines that on extension intersect at a single point in the image plane called vanishing point or point at infinity. Alternative definition. The vanishing point of a line depends on the orientation of the line and not on the position of the line. The vanishing point of any given line in space is located at the point in the image where a parallel line through the center of projection intersects the image plane. Vanishing line. The vanishing points of all the lines that lie on the same plane form the vanishing line. It is also defined by the intersection of a parallel plane through the center of projection with the image plane. Orthographic projection. It is the projection of a 3D object onto a plane by a set of parallel rays orthogonal to the image plane. It is the limit of perspective projection as f tends to infinity, that is, f by z tends to 1. Orthographic projection equations: small x equals capital X, small y equals capital Y. Using matrix notation, xh, yh, zh, w equals 1000, 0100, 0000, 0001 into x, y, z1. Verify the correctness of the above matrix. Homogenize using w equals 1. X equals xh by w equals capital X. Y minus yh by w equals capital Y. Properties of orthographic projection. Parallel lines project to parallel lines. Size does not change with distance from the camera. Weak perspective projection. Perspective projection is a nonlinear transformation. We can approximate perspective by scaled orthographic projection, that is, linear transformation, if the object lies close to the optical axis, the object's dimensions are small compared to its average distance z dash from the camera, that is, del z is less than capital Z by 20. Weak perspective projection equations. X equals xf by z, approximately equal to xf by z bar. Y equals yf by z, approximately equal to yf by z bar. The term f by z is a scale factor now. Every point is scaled by the same factor. Using matrix notation, xh, yh, zh, w equals f000, 0f00, 0000, 000 z bar into capital X, Y, Z1. Verify the correctness of the above matrix. Homogenize using w equals z dash. X equals xh by w equals fx by z bar. Y equals yh by w equals fy by z bar. Stereogeometry. In stereogeometry, we are going to see about epipoles, epipolar and epipolar planes. Epipole. The image in one camera of the projection center of the other camera is called as epipole. Left epipole. The projection of OR on the left image plane. Right epipole. The projection of OL on the right image plane. Epipolar plane. The plane defined by P, OL, OR. Epipolar line. Intersection of the epipolar plane with the image plane. If the line through the centers of projection is parallel to one of the image planes, the corresponding epipole is at infinity. Stereo basics. The camera frames are related by the translation vector T equals OR minus OL and a rotation matrix R. The relation between PL and PR, projection of P in the left and right frames, is given by PR equals R into PL minus T. The usual equations of perspective projection define the relation between 3D points and their projections. PL equals FL by ZL into PL. PR equals FR by ZR into PR. Epipolar constraint. Given PL, P can lie anywhere on the ray from OL through PL. The image of this ray in the right image is the epipolar line through the corresponding point PR. The correct match must lie on the epipolar line. Establishes a mapping between points in the left image and lines in the right image, and vice versa. Property: all epipolar lines go through the camera's epipole. Importance of epipolar constraint. Corresponding points must lie on conjugate epipolar lines. The search for correspondences is reduced to a 1D problem. Very effective in rejecting false matches due to occlusion. Ordering. Conjugate points along corresponding epipolar lines have the same order in each image. Exception. Corresponding points may not have the same order if they lie on the same epipolar plane and image from different sides. Estimating the epipolar geometry. The essential mixture E. The equation of the epipolar plane is given by the following coplanarity condition, assuming that the world coordinate system is aligned with the left camera. PL minus T raised to the power of T into TX PL equals 0. Using PR equals R into PL minus T, we have R raised to the power of T into PR whole raised to the power of T, TXPL equals 0. Expressing cross product as matrix multiplication, we have R to the power of T, PR whole raised to the power of T, SPL equals 0, or PR raised to the power of T, RSPL equals 0, where S equals 0 TZ minus TY, minus TZ 0 TX, TY minus TX 0. The matrix S is always rank deficient, that is, rank S is 2. The above equation can now be rewritten as follows. PTR EPL equals 0 or PTR EPL equals 0, where E equals Rx is called the essential matrix. The equation PTR EPL equals 0 defines a mapping between points and epipolar lines. Properties of the essential matrix. Encodes information on the extrinsic parameters only. It has rank 2. Two non-zero singular values are equal. The fundamental matrix F. Suppose that ML and MR are the matrices of the intrinsic parameters of the left and right camera, then the pixel coordinates PL and PR of PL and PR are PL equals ML into PL, PR equals MR into PR. Using the above equations and P raised to the power of T, REPL equals 0, we have P raised to the power of T, REPL equals 0, where F equals M minus 1R raised to the power T, EM minus 1 equals M minus 1R raised to the power T, RSM minus 1L is called the fundamental matrix. Properties of the fundamental matrix. Encodes information on both the extrinsic and intrinsic parameters. It has rank 2. Computing F or E, the 8-point algorithm. We can reconstruct the epipolar geometry by estimating the fundamental matrix from point correspondence only. Each correspondence leads to a homogeneous equation of the form shown on the screen. We can determine the entries of the matrix F up to an unknown scale factor by establishing n cubed 8 correspondences. AX equals 0. It turns out that A is rank deficient, that is, rank A equals 8. The solution is unique up to a scale factor, that is proportional to the last column of V, where A equals UDVT. Input n corresponds with n cubed 8. Construct homogeneous system AX equals 0, where A is an n into 9 matrix. Suppose A equals UDVT is SVD. The entries of F are proportional to the components of the last column of V. Enforcing the constraint rank F equals 2, singularity constraint. Compute the SVD of F. F equals UFD FVT. Set the smallest singular value equal to 0. Let D-F be the corrected matrix. The corrected estimate of F is given by F equals UFD FVT. We need to normalize the coordinates of the corresponding points, otherwise A has a very bad condition number which leads to numerical instabilities. Homogeneous positive representation of lines. A line AX plus BY plus C equals 0 is represented by the homogeneous vector below, projective line. Matrix A, B, C. Any vector K represents on same line. Only the ratio of the homogeneous line coordinates is significant. Lines can be specified by two parameters only, that is, slope or intercept. Y equals mx plus I. Rewrite ax plus by plus c equals 0 in the slope-intercept form. Y equals minus a by bx minus c by b. Homogenization rule for lines ABC is to minus a by b minus c by b. Some properties involving points and lines. The point x lies on the line if x power t L equals 0. 2 points define a line L equals P into Q. 2 lines define a point P equals L into M. Duality. In homogeneous projective coordinates, points and lines are dual. We can interchange their roles. For example, 0, minus 1 lies on 2x plus y plus 1 equals 0. The point 0 minus 1 is represented by x equals 0 minus 1, 1. The line 2x plus y plus 1 equals 0 is represented by L equals 2, 1, 1 matrix. X raised to the power of t into L equals 0.2 plus minus 1 into 0.1 plus 1.1 equals 0. Finding the epipolar lines. The equation below defines a mapping between points and epipolar lines. P to the raised to the power t, R, F, P, L equals 0 raised to the power t. For case 1 representations, please refer to the equations on screen. For case 2 representations, please refer to the equations on screen. Locating epipoles from F. For case 1 representations, please refer to the equations on screen. For case 2 representations, please refer to the equations on screen. Rectification. This is a transformation of each image such that pairs of conjugate epipolar lines become collinear and parallel to the horizontal axis. Searching for corresponding points becomes much simpler for the case of rectified images. To find the point corresponding to left image, we just need to look along the scan line in the right image. Disparities between the images are in the x direction only, no y disparity. Main steps, assuming knowledge of the extrinsic and intrinsic parameters. Rotate the left camera so that the epipolar lines become parallel to the horizontal axis. Epipole is mapped to infinity. Apply the same rotation to the right camera to recover the original geometry. Rotate the right camera by R. Let's consider step 1. The rest are straightforward. We will construct a coordinate system E1, E2, E3 centered at OL. Aligning the axes of this coordinate system with the axes of the image plane, coordinate system yields the desired rotation matrix. E1 is a unit vector along the vector t, as per equation on screen. E2 is chosen as a cross product of E1 and the z-axis, and this can be represented as per equations on screen. Similarly, choose E3 as a cross product of E1 and E2. E3 equals E1 into E2. The rotation matrix that maps the EPI poles to infinity is, and the representation is given on the screen. Note: rectification can also be done without knowledge of the extrinsic-intrinsic parameters, but it is more complicated. Multi-view geometry. Generic problem formulation. Given several images of the same object are seen, compute a representation of its 3D shape. Images of the same object are seen. Arbitrary number of images from 2 to thousands. Arbitrary camera positions, isolated cameras or video sequence. Cameras can be calibrated or uncalibrated. Representation of 3D shape. Depth maps, meshes, point clouds, patch clouds, volumetric models, layered models. Feature matching to dense stereo. Extract features. Get a sparse set of initial matches. Iteratively expand matches to nearby locations. Use visibility constraints to filter out false matches. Perform surface reconstruction. The third view can be used for verification. Pick a reference image and slide the corresponding window along the corresponding epipolar lines of all other images, using inverse depth relative to the first image as the search parameter. How to find disparity of an image? Disparity x or x dash equals b minus f by z, where b is baseline, x and x dash represent disparity, f is focal length, and z is the depth of an image. Disparity is proportional to the baseline and inversely proportional to depth. For larger baselines, we must search larger area in second image. This is used to allow multiple users to view single model images. Conclusion. In this chapter, we have covered the following in detail: monocular imaging system, orthographic and perspective projection, camera model and camera calibration, stereo and multi-view geometry, binocular imaging systems.